Hello everyone, welcome to my YouTube video. Today I am demonstrating how I completed this project with Silicogen AIE. So I gave AI an prompt which says, I am trying to build I²C Controller with Slave BFM having arbitration flags and clock stretching, and I have specified some rules for you to follow and also requirements documentation, and also use skills you want. The AI started to analyze my request, and it also read my files, which are files for configuration. I set up for this project, and it went through my requirements and started analyzing my request. Silicogen AI then started to look for tools which it needed, like OpenRoad, I²C, and I²C, and made sure all are properly installed and are accessible for this project. Silicogen started by defining the full microarchitecture in structured design documents before writing a single line of RTL, covering every interface, state machine, and timing requirement up front. From those documents, it generated a clean three-level hierarchy: register file, byte controller, and bit controller. Each module built bottom-up, with arbitration detection and clock stretching handled as dedicated sub-modules. Every design decision, from the four-phase clock scheme to the double flop synchronizer, was documented and verified against the official I²C specification before the RTL was ever synthesized. The main goal of Silicogen AI is to help user to design architecture with full research and help user understand and debug any problem statements. Silicogen AI has completed the research and created full architecture required for the project. Now user can view the documentation and ask any doubts related to the architecture and user and request, any changes related to it. And now Silicogen proceeds to run simulation so it can understand which bugs it is going to face. With the architecture locked down, Silicogen turned to the next challenge. How do you actually verify a multi-master I²C controller with arbitration and clock stretching? A simple directed test bench would cover the happy path, but it would never stress the edge cases that matter in silicon. So Silicogen evaluated the options. A pure RTL test bench was too rigid. Formal verification alone couldn't model the full bus behavior. UVM gave the right balance, structured, reusable, and built for the kind of constrained random stimulus that would actually find bugs. The decision was UVM, but that changed the strategy immediately. With UVM in place, the first practical step was updating the makefile, adding compile targets for the UVM library, the RTL sources, the test bench components, and the simulation runner, so everything could be built and run with a single command. Then Silicogen began generating the RTL, module by module, bottom-up. The leaf modules came first, then the controllers, and finally the top level that wired everything together. 7 modules in total. The bus synchronizer, which double flops every incoming SCL and SDA signal to eliminate metastability. The arbitration detector, which compares what the master drives against what the bus actually shows. The clock generator, which runs the 16-bit prescaler and produces the 4-phase enables. The bit controller, the 18-state machine that directly times every edge on the I²C bus. The byte controller, which manages the shift register and sequences full 8-bit transfers. The register file, which gives the host clean read-write access to configuration, commands, and status. And finally, the top-level controller, which integrates all 6 modules into a single synthesizable block with a standard host interface on one side and open-drain I²C pins on the other. Each module was written to match exactly what the architecture document specified. No surprises, no drift from the original design intent. Once the RTL was complete, the user asked Silicogen to revalidate everything against the original requirements. Silicogen launched parallel agents simultaneously. One auditing the arbitration logic, another checking the clock generation, and another tracing the FSM state transitions against the documented specs. 2 bugs surfaced. The arbitration detector was checking SDA 1 phase too early, before the bus had fully settled. The user gave Silicogen the green light with the RTL validated. Silicogen started simple. Basic directed tests first. A single byte write, a single byte read, a repeated start, and a stop condition. Each one confirming that the fundamental bus operations worked exactly as the spec defined. Then it layered in the edge cases, clock stretching scenarios, NAC responses, and back-to-back transfers without releasing the bus. It all ended with the smoke test. One clean end-to-end transaction. After completing and simulating the UVM test bench, Silicogen hit an immediate error. The UVM package was missing from the compile order, breaking the entire build. It traced the root cause, added the correct UVM package import to the makefile. Even after resolving the package issue, syntax errors kept surfacing across multiple files. Mismatched port declarations, incorrect macro usage, and UVM phase hooks that weren't wiring up correctly. Silicogen stayed in the loop, reading the compiler output, tracing the exact line, editing the file, and recompiling, iteration after iteration without stopping. When the user permitted web search, Silicogen went further, pulling documentation and fixes directly from online references, applying them autonomously, and continuing the debug cycle. With the smoke test done and coverage testing underway, Silicogen hit a wall of deeper bugs that only surface under real multi-phase transactions. The Slave BFM was using asynchronous edge detection. Silicogen rewrote the slave entirely as a synchronous 7-state model locked to the system clock. Then the read path turned out to be broken at the silicon levee. And finally, false stop conditions were being detected when the slave released SDA during its own ACK. Because on an open drain bus, the slave's own SDA transition looks identical to a stop. A self-release filter was added to exclude those. All 5 UVM tests, smoke, directed, random, arbitration, and clock stretch, passed clean after those fixes. Silicogen completed this project from architecture to netlist successfully. Thank you everyone, and please subscribe.